Okay, so for this problem, it says Dr. Thanos, data scientist and self-described nihilist, recently published a paper titled The Snapping Point of the Universe, Why Rates of Population Growth Point Towards Imminent Destruction. In his paper, Thanos explains that in many planets, the increasing population count is leading to a diminished quality of life. He is convinced that his findings will drive sweeping reforms in intergalactic law, leading to a better life for all organisms. Thanos turns to you, his confidant, to do some investigation. He would like some concrete evidence for his findings to present to the Association of Venge's Research Society. The society, one of the galactic leaders in egalitarianism and social justice, is holding a special panel to discuss Thanos' findings. As this involves the chance of actual legislation being passed, Thanos is convinced that the panelists are going to be a tough sell. He has to investigate several data sets to see if they could potentially be helpful in supporting his argument. Thanos hands you the data for several planets. On each planet's file, you read that the planet currently has a population P. Its population grows by a factor of R times per year, and its annual food production in F in tons. All food produced in a year must be consumed that year. It cannot be saved. Assume that each individual consumes 1 ton of food per year, and that the population for each planet each year is always counted as a whole number, rounded down. Given this information, your task is to find out the number of years a planet has remaining before its population is no longer sustainable by its food production. Okay, so for this problem, each person consumes 1 ton of food in a year. So if in a given year a population has less than or equal to the amount of tons of food it has that year, then the planet is able to sustain itself. However, the population grows R times per year, meaning that whatever R is, you multiply that by P, and the next year that's going to be the population. So if that ever grows larger than the amount of food it has, then the planet will not be able to sustain itself. So let's just go over here. So the first line of input consists of a single integer t, the number of planets that need to be analyzed. T lines follow, so this is t right here, and then here are the t lines. The ith of which, meaning whatever line you are looking at here, consists of 3 space-separated integers p. This is the population, the initial population. R, so by how many times it grows each year, and then F, the food production it has for each year. So the idea here is you're going to keep multiplying this number by 3, and then count how many times you keep multiplying this number by this number until it exceeds this number. So let's just go through this example, I guess. So for the first year, we're good. 1 and 9, so it clearly is able to sustain itself. It has 1 population and 9 tons of food, so they're able to survive. The next year, so year 1, so I guess for 1 year it's able to sustain itself because it grows by a factor of 3, so it's 3 times 1. It has 3 people, and it has 9 tons of food. So after a year, it's still able to sustain itself. After 2 years, it then has 9 people, which they're still able to sustain themselves because they have an equal amount of tons of food for their population. On the 3rd year, they do 3 times 9, so it's 27, and it exceeds 9. So after 3 years, the planet is no longer able to sustain itself. Similarly for this one, 2 times 2, so it's 4. 4 times 2, so that's year 1. 4 times 2 is 8, year 2. 8 times 2 is 16, year 3. So 16 is equal to 16, so it's still able to sustain itself. And then 16 times 2, 32. It's no longer able to sustain itself, so it took 4 years for them to not be able to sustain themselves. Same thing for this. After 1 year, it has 10 people because you multiply it by 2. So 2 times 5, and then 2 times that is 20, which exceeds this. So I'm going to see if I can solve this in Python here. I'm going to open up Visual Studio Code. And we're going to make something called Thanos.py. And let's put this to the side here. . Okay. So we have this first line of input called t, or this first number. So I'm going to say t is equal to the int of the input. And then we're going to have t lines that follow. So for each line, sounds like a for loop. So for I in range t, we're going to get those three numbers. So let's call this the same as, or I guess we could say initial population. That's this first number right here. Growth rate and food supply. And then here's a little trick. So we have the input, which is the line, this line. And kind of like last time, we're going to split that. So that looks like an array of 3 strings. So I'll show that right here. Looks kind of like 1, 3, and 9. And then, if you remember from Racket, you have this function called map, and this will apply whatever this first thing is to each item in whatever array is here. So this actually is an array of strings, so it will apply the function int, which turns a string into an integer, or a number, and it'll do that for each item. So after we've applied this map int to this array of strings, this will just be numbers now. And by the way, in the description of each of these videos, I also have this code on GitHub. So if you want to take a look there, you can. I'm going to make this a little bit smaller. That's a bit too small. Drag that over a little bit. Okay. Okay, so the way I'm going to do this is I'm going to keep multiplying this initial population, so I'm going to keep growing it until it grows past whatever the food supply is, and then I'll keep track of how many times I've multiplied it. So in order to do that, I'm going to start this little variable called number years, and I'm going to say while initial population is less than or equal to, because equal to, as we've seen, is still sustainable. Food supply, I'm going to keep multiplying the initial population by the growth rate. And then for each time that we multiply it by that growth rate, we're also going to increment number of years. All right. And then at the end, we're going to print the number of years. And yeah, so I think that looks good to me. Yeah, so it's going to print for each time. So it's each line of input, we're going to print out the number of years they survive. I'm going to run this. Oh, I spelled this wrong. Okay, that looks correct. Okay, so I'm going to put this in. Stop high. And submit. Cool. Okay, so I'm also going to do this in Java just because there was a issue I ran into this when I was trying to solve this in Java that I think will be interesting to point out. Okay, so for Java, we're going to do import java.io.scanner. That's right, right? Oh, is it util? Yeah. Okay. And then we have class Thanos. We want our main method. then we want scanner. And this is all the same stuff as I talked about last time. You make this scanner object, which allows you to input into the command line when you run this Java program. And then we have this int t, just like last time. So I'm going to call it int t is equal to, so scanner, next. And I want to parse that as an integer. Excuse me. All right. So now we have t for the test cases. Now we're going to go through each test case. Okay, so just like last time, I'm going to read in the line string is equal to scanner dot next line, then string array split input is equal to input dot split, and then int initial population. That's the first number again. This 1 here. So I'm going to say it's split input 0. And then int growth rate is the split input 1. What is this giving me here? Alright, we need to parse this as an integer. And then the last item here is the food supply. And then again, to kind of show you what's going on here, 139, and then 139, just like last time in the first video. Okay, now the same thing as this, we're going to use this while loop. So while initial population is less than or equal to food supply, we're going to multiply initial population. So times equals is the same thing as saying initial population is equal to initial population times growth rate. It just makes it a little shorter. So same thing like that. Did I spell it wrong? No. Okay. And then we're going to have this variable called numYears. And then down here, we're going to increment it every time we multiply by that growth rate. Then at the end, we print out the number of years. Okay. Now, okay, so let's see if this works. I mean, it's doing the same thing as this is doing. Again, run Java. Cool, looks like it's working. So Java, let's do that. Okay. So here's something that kind of was kind of tricky for me here. Okay, so I'm going to give you an example of what might be going on here. So if I have an integer, integers in Java are able to hold up to 32 bits. So the limit on this population, or this population and this rate is both 10 to the 9th. So I mean that's small enough to fit within an integer. So let's see, 1, 2, 3, 1, 2, 3, and then 1, 2, 3. And then let's have another integer called int y. If I try to define an integer, z, as something, way too big, Java will give me an exception saying it's out of the range of an integer. So even if I tried to run this, let's just try to print all of these. So print, and then these two will be able to print, but this will give you an exception. So as you can see, this is out of range. So it just gives me an error or an exception here. However, if you multiply two integers and the result is too big, Java does not tell you that it is too big. It just gives you some nonsense because you've went outside of the limits of integers. So if I do instead system.out.println x times y, and we know that to be 18 zeros, let's try that. So it gives me this big negative number. And when we're doing this Thanos problem, we are multiplying initial population, which again can be as big as 1 billion, by this growth rate, which again can be as big as 1 billion. And then we're trying to see when it's less than or equal to the food supply. If we're getting all these random negative numbers and whatnot, it may never get bigger than the food supply because it's growing too big to be an integer. So what we can do instead is we can make this initial population a double. And that will be big enough to fit those kinds of numbers. So if I'm just going to show you here. It gives me 1 times 10 to the 18th. So now let's try to input this. And we are golden. So just to kind of put into perspective some of the issues you can run into with Java, I hope you learned something from that. It actually stumped me for a while, as you can see here. I wasn't sure why that was going on. But yeah, so this was just sort of a math problem. A little bit more interesting than the last one, but you learn something from everything here. So hope this helped, and I'll see you in the next one.